Okay, let's go ahead and get started. Today, we're going to cover stacks and queues. They're going to be the first abstract data type. It's not going to be an exact data type like an array or a linked list. What it is really just an abstract idea about how something occurs, namely stacks and queues. And you usually use some other concrete data structure in order to implement this. Now, this is going to be the first time where I will show you that not all labs have to be hard. They can actually be very simple if you think about it ahead of time and then implement it. So we're going to let's just go into stacks and queues because you'll probably at least address this a little. Have y'all done stacks?
Yeah. We didn't like do a whole lot with them, but we have touched on that.
Okay, did some, and then a queue. Anyone from the UK? Oh, okay. Cool. All right. Queues. All right. Now, here's the other thing. Did y'all do recursion?
I mean, we did. Yeah, we did recursion on procedural.
Oh, and procedural, but how about OOP? No? Okay. All right. We're going to learn a bunch of stuff. That's great. Stack. Data structure which elements are added and removed at one in only, aka last in, first out. So you can think of it as a stack of plates where you can only put something on top, or you can take something off the top as well. But you're only operating on the top of the stack. So you push an element onto the stack and you pop it. All right. Everyone with me so far? Hey, look, a stack of coins, a stack of trays, a stack of boxes. Knows those boxes have lids, because at first that image confused me. And then a stack of books. So the top, of course, in your stack of books is applied math. Now, if you can only operate on the top and you want to get to your English book, what do you have to do? Yeah, you have to keep removing until you get down there. All right, we're doing great. Empty stack is on the right. Good. Push A, push B, push C. And then there's an operation called peek that's very common where you just see what's on top because you can always look at the top element. Now, with the stack, you cannot look further down the stack. You can only look at what's on top of the stack. And then you can push D on top. And then if you want to pop the stack, it just removes D. Notice pop did not give you D. It simply removed the top element. If you wanted to see what was on top, you'd peek and then remove it would be a push afterwards. So keep in mind that in general, those two operations are different. All right, they do push. Up here, they're calling it top and pop. It's great. Top and pop. Let's actually, okay. So we have a stack. What can we implement a stack with? Okay, calls, yes, but how would we store the data? What could we use? What's that? We can use, okay, so there's an array. Well, we have vector, right?
Yeah.
Right, so we could use a vector. What's the other thing we've used? A linked list, okay. So we have two data structures. Could we use either of them to implement a queue?
Yes.
Yes. Thank you. All right, yes. We can use both of them to implement queue. They're going to go through an array first. All right, this is great. Wow. Wow. Are we going to say anything useful? Here we go. Picture, finally. So with pictures, let's at least think about it. Stack, this is your object, or your object, your stack object. Up here, they're going to keep track of your max size, and they're going to keep track of stack top, which is the index of what the top is, and then your list is going to point to where the array starts. So stack top being 4, notice element 4 doesn't have anything. That's where the next element is going to be added. Good morning. And then it currently has 4 elements in there, 0 through 3. Great. So, we're going to have pictures. Yeah, that's the one initialized. What would we do if we wanted to add E? Whoops. To this one. There we go. Add E to this one.
We would have to pop the other elements and then.
Let me say push E. How about that? We're going to push E onto the stack. Where does it go? On the top, which is slot 4. So it would put the E, let me use my mouse pointer for the people at home. It would put E right here, and then what else would it do? Yeah, there we go, increment stack top. Anyone see an issue with this implementation?
I mean, it seems like the bigger data structure, the slower it would be, because you would have to, if you want to find something specific near the middle.
Well, you're always operating on the top, so it's not so much slower. But, well, let's keep going. Maybe it'll become a little clearer. So in this slide, they have reinitialized the stack. Notice that the stack still has A, B, C, D. But if I were to push E, where would it go? 0, and it would overwrite the A. And then stack top would become 1. Because stack top is currently 0. This is just what was in there already. We reinitialized the stack. So the list would point to the bottom, put an E right here, and then stack top would be number 1. Yeah, I'm just saying this is initialized stack. So over here we're saying this is a pretend stack with 4 elements. You could still have the same piece of memory, but if we reinitialize the stack, all we did was take stack top and set it to 0, and now we've cleared the entire stack. Yeah, we don't really care that A, B, C, D are already in there, right? We don't have to overwrite that. We already know by stack top that there's no elements. All right, so yeah, if it's empty, if it's equal to 0, if it's full, the stack top equals max stack size, so that should be a hint. Oh, cool, here we go. This is terrible. Sorry. Pushing Y. Right, we'll put that there. Do we get another image? We don't. All right, what's the problem with this implementation?
What if we try to push to something which is already master size?
Right, so what if we have, our stack has 100 elements and we push another item? What do we need to do? Well, we don't want to remove anything because we want to keep track of the stack.
Which would involve creating a new one.
Right, so we'd have to increase the size of the array, which would involve creating a new one. So let's go and start doing our good old big O analysis, which we should always be thinking about. Yeah! Yes. Where's the glare? Oh, this marker's terrible. I'm not going to make it. Oh, so close. All right, so we have push, we have pop, there we go. And we have array. All right, yeah, that's a nice marker. So if we push, what is it on average? O of 1, right? Because normally there's a space there and we're good to go. Worst is what? O of n, because we have to recreate the entire, where n in this case is the size of the stack. Okay, how about pop?
Just build one.
Yeah, O of 1. And we'll also do top, sometimes referred to as peak. O of 1, okay, good. All right, so really with the array, we just have this bad situation where we have to reallocate the entire array. Okay. So what other data structure could we use? A linked list. Good morning. Need anything?
Just checking.
Oh, just checking? Okay.
Good job. Good job. Finish? Okay.
Thank you. Excuse me.
Alrighty then. So we'll do a singly linked list for now, in case we need to do doubly. Let's go and hopefully the slides give us some nice pictures of what this would look like. Wow, we're just going to go through a lot. Here we go. Let's look at the linked list, the linked version. You understand why I skip all that code in a bit. So stack top would just be a pointer to a node, right? And then y'all used to arrays. Let me go ahead and draw this out on the board with the linked list, because this is still something a little new to y'all. So if we want, we have stack top, and we'll have that point to currently null, which means the stack has how many elements in it? Someone said it. 0. Great. Let's say we want to push. Can y'all see that? Or is that not on there? It is not on there. Okay. Let's say we want to push 42. What do we do? Yeah, we're going to do a linked list implementation, singly linked list.
So create a node.
Correct. We first need to create a node. Obviously, we'll have the value 42, and where should it point initially? Null. Okay, great. Great. Now what do we do? Okay, so the head now needs to point. Okay? All right. Let's push 17. Mark that we're done. What do we do here? First, make a node, right, with 17 in it. Where should it point? Null? Okay, we'll start with that. All right, now what are we going to do? We're doing, oh, we could have entail. Well, we can actually accomplish this with just one pointer. Anyone see what to do? Here's the big hint. What if we had this point to this guy?
Then we just make the head point to
Yeah, and then we just update the head pointer to point to that. Because now if we do peak, what's the answer? Yeah, 17. Because that's where the top pointer is.
So this requires less pointers.
Hmm?
So this requires less pointers.
Yeah, singly linked list. We're just doing this with pointers. Let's go ahead and push one more element, just to make sure it's kind of clear what's going on. Push. Let's do 9. What do we do? First thing, make a node. We'll put in 9. Where does it need to point to?
17.
Which is what stack top is, so we have a pointer there. Then what do we do?
What is that?
Yeah, we put stack top up here. All right. Now let's do pop.
To make the stack point to the next element.
Okay. Yeah, so we just have stack pointer equal stack pointer dash next. Right? But what else do we need to do? Hmm? We need to delete 9, right? So let me make this a little clearer what actually happens, because if you did it this way, you would have a memory leak. What you probably should do is have make a temp pointer. Point here. Then have the stack pointer go down here. So this would be 1, this would be 2, and then step 3 would be delete temp PTR.
Some text is cut off.
Oh, okay, great. Yep. All right, so then that would get rid of this right here. And then how many elements are in the stack? 2. Okay. Any questions about this? Yes.
Weird question about nodes. So, how do you do that, like, in, I guess, coding? Like, I know you can draw it up and do that, but how would you make a node in, like, C++, if that's a thing?
Sure. Yeah, we can. Do y'all want to see the code for a single linked list? Sorry, the list implementation of a stack, or would y'all prefer an array actually? Does the array one make sense to y'all? I'm assuming y'all have done arrays for so long, I don't need to do it again. But unless someone really needs it.
I'd like to see it.
You like to see both? Oh, well, now we're going to have a long lecture thanks to you. No, I'm kidding. I'm kidding. All right. Stack. Let's go do a stack. Let's see. Source and test. gvim source array. Oh, actually, not array. Stack dot cpp. Yeah, let's do HPP. All right, so let's just make a simple stack here. And we have, ooh, that didn't work out well. Let's try that again. There we go. So we're going to do it with an array first? Sure, why not? We'll make it integers just for the time being. We probably should keep track of the size. And then, what do we want? Top? Okay.
Can you make it a little bigger?
Of course. How's that? Good? All right. So we want to do void push int val void pop, and we'll just do int. You want to do top or peak? Top? Okay. You know what? We're going to also have peak, just for fun, just for the fun of it. Y forward down tab new source stack.cpp. Let's go paste all that. All right, let's go ahead and create a quick main. Ooh, someone's printing. RV. All right, let's see if any of this compiles. Not quite. After class decoration. No one caught that? Hey, look, it worked. Great. First try. Okay, so we want to do s dot, we'll do what's on the board. What do we do? Push 42. 17. And then what was the last thing we pushed? 9? Okay, great. Do s dot, I will do top. What do we got? S dot top. And then we'll push it again, and then we'll pop it. Okay. Oops. Pop, and then actually I should do the same thing. All right, let's see what happens. Make. Oh, good. Dot pop. That's right, because we don't pass it anything to pop. We'll need to include IO stream. Oh, great. Let's see if it runs. All right, that's obviously not right. Probably because we haven't, coded anything. But we started at least with the test case, a simple test case, but a test case nonetheless. We should also have a constructor. Constructor, all right. All right, so we have marray needs to be something. And what else do we have? M size. We got, oh, M stack. Let's go and just copy those two guys over. Okay. We'll do the easy part first. What should M size start out to be? 0. How about the top? All right, we're doing great. M stack, we're using array, so we need to do what? Create a what? Yeah, new int. How big are we going to make it? 32? Okay, sure, why not? Why not? We're going to have to fix this in a bit. Can anyone see an error already? Or an issue? Yes. So size, all right, so we're going to use size to dictate how many elements can be held. So we're going to have, right, so if we have size to be capacity, maybe we should do this. Right? And that would make a little more sense as to what we're actually saying here. Oops, 32. And then down here, we're actually going to say M capacity. Why did I write M capacity there instead of 32? Very important. Very important software engineering question, not a theoretical math question.
If you changed it in one place, it goes through. So you're
Yes.
changing it once.
We only have to change it in one place. Even though it was 2 lines down, trust me, I have had to debug people's code where they literally did not change the second place. So this is a defensive measure to make sure you don't make mistakes. Oh,
Protecting you against yourself.
against what?
Protecting yourself against yourself.
And other programmers that are going to modify your code, yes. You're not going to be the only one doing this, trust me. All right, let's push. What's that? Yes, so what am I typing?
So M stack, they have M tops, the index of
Nice, plus plus, okay. Okay, wow, that's amazing. All right, we're not done with that, but we're going to leave that for now. How about pop?
M top minus minus.
All right, M top minus minus. Top, well, we're going to return something.
Return M stack M top.
All right. What should peak be? Think about this.
Top.
Yes. Again, why am I calling top and not return M stack M top? I'm just trying to make sure it's perfectly clear. Yes.
I'm curious why pop does not return anything. 'Cause
Okay.
when you normally-
Yeah, hold on. I'll answer that. I'll answer that question in a moment. Why is peak calling top?
Because if you change it in one place, you'll not have to change it.
Okay, good. Everyone seeing that? Be consistent. I'm just trying to help y'all out here. Right, so if you change M top, you don't have to change peak. Which, by the way, there could be, 500 lines of code right here. Right, Perry? Good. All right, your question, why don't we have top return something? There are different ways to implement a stack. This is actually the general conceived C++ way to do it. You want pop and peak, or top, sorry, to be separate functions. In Java, pop actually does return the top element. In C++, by convention of the way we implement things, it does not. Convention. We decided it. When you use a language, it is a good idea to usually write a book called like Effective C++, Effective Java, and it's going to tell you all the little things that they suggest doing it. And by convention, just to make your code more readable for everyone else. All right, that looks like a good start. Let's go ahead and make it and run it. Top is 0, top is 9. Let's see, does that make any sense? So I push 42, push 17, and then top is 0, push 9. Yeah, so we got a problem already. Wow, that was fast. Anyone see it?
Is it because they're setting the inside of the array to M top?
What's M top actually?
Is where the next
The next element would go. Do we want to return the next element? No. Oh, okay. And hey, look, now I only have to change it in one spot. All right. Aren't you glad you wrote a test case?
Yeah.
Oh, nice. Thanks. Thanks. Okay. So let's go and do at least a couple more test cases because I've had people ask about that, and I love copying from other code because I don't like rewriting things. Unlike y'all do. Do y'all?
No.
No, I didn't think so. Thank you, Damon. We'll do, what am I going to call it? I'll just call it the stack test. All right. Oh, did I put in source? Tab new, test, stack test. There we go, perfect. Ooh, test one. Let's include stack.hpp, stack s. I don't know why I put a right there, but we'll go s.push, ts assert, s.top equals, I didn't push anything. Huh, that's cute. 42. It's 42. We'll push 17. What should the top be? All right. And we'll push 71. What should top be? 71. All right, great. Now we've got 3 of them in there. Let's start popping.
I thought when we did pop, we had to like make a temp.
That's a linked list implementation. This is different. What should top be at this point? 17. Great. And what should pop be at this point? 42. All right, and there. First test should be the happy path. AKA, this all makes sense, right? Yes.
Yeah. So we need to test that for when we try to like top or do, and the array has 0 elements. We need to not like, return the negative first.
Yeah. When you're being a tester, first thing, like he's pointing out, we did the happy path first. Go ahead and compile and make sure the happy path passes. And I think I called this stack test. Let's go ahead and look. What did I call this thing? I called it stack test. Oh, I see the problem. Huh. I'm going to call it stack manual test. There we go. All right, it passed. Good. Now we need to test things that may not be as good. So stack s. Let's do s.push. We'll push 42. S.pop. S.pop. S.push. Oh, we got 17. And then we'll do assert s.top equals 17.
Why call pop twice?
Yeah, what should happen when you call pop twice? Is that something we want? Is that something that you would expect to happen?
Nope.
Nope. But could it happen?
Yep.
Therefore, will it happen?
Maybe.
Yes. The answer is yes. Okay, we got it? We're good?
Got it.
We're good. You have to, just like a small child using your code, your programmers are going to abuse your code a lot, and it's not going to make much sense.
Is that going to remove 2 different numbers from it?
Let's see. Why don't we just run it? What happens? Oh, probably should call top with open and close parentheses. You know, simple things in life. Hey, it ran just fine. Okay. Well, that's good. I think. Maybe. Possibly. Let's make this fun. Oh, this should always be in your code. Hey, it still passed, so we're doing great, right? Well, let's Valgrind it. Hey, it took it. Wow, definitely lost. Oh, wow, what does that mean?
Being deleted.
So we are subtracting. Okay. All right, yeah, let's go and fix that one first. Let's see, what do we have? Sometimes I like to put my destructor right after my constructors. What are we doing? Yeah. All right, let's see if we can make the. That way, it's a again, you're defending against your future self. By setting it to null, you're explicitly stating that mstack is no longer pointing to anything useful. Beforehand, it is. So.
Was the delete the new way since the structure was going to be called one day?
Correct. In general, yeah, this line that I'm currently on is superfluous. In my current, in the current way the code is written, this line is 100% superfluous and is technically not necessary whatsoever. I will tell you right now, do it this way anyways, because this code will be managed, and someone will decide after your constructor to do something like mstack arrow blah 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 equals something. They will do it.
Okay.
They're just going to do it. Just trust me. So if you put null, then it's going to instantly throw a null pointer. Well, not a null pointer. Segfault. The debugger will say this pointer is null, and then they'll find their error quickly. Otherwise, you're going to have weird memory situations, which will take way, way longer to fix. All right, so I think this is still going to fix our issue. We're not getting any problems, which is actually quite amusing. Oh, no, here we are. Mismatch free delete. Oh, probably because it wants the this guy, which is fine. We'll go fix that real quick. All right. Huh. No leaks are possible. No memory errors? Wow, that's amazing. All right, so we'll just continue on, even though that actually makes absolutely no sense. Yeah, it doesn't. All right. Let's see, what else can we do? Oh, I know what we should do. We'll do the other one. The other way. We'll go and create a quick little stack. We'll and we'll go ahead and push I. And when this is all done, what should top be? All nines, right? 4 nines.
Here since the array size is 32.
Oh, wow, that was, oh, wow, it just blew up. Hold on, let me clear my screen so this will be easier to read. Boom. Double free or corruption. Wow, it did not like that. Oh, so we're getting some weird memory issues. Let's see if Valgrine's going to help us out any. It may or may not. Whoa, I haven't seen this one before. This is cool. Okay, so push int invalid right of size 4. Oh, it's even going to tell me? Stack.cbp line. So we're doing an invalid right of size 4 on line 18. Okay, yeah, there we go. What's the problem? No, because the deconstructor hasn't been called, so it's still valid.
Well, the mstack size is 32, so once it reaches that, it can't write to the array.
Everyone got that? How many elements can be stored in this array? 32. How many elements is my test code adding? 10,000. Is that more than? That's more than 32. Sorry. Rhetorical question. Is it? Are we really doing? Okay.
Is that how numbers actually work? Like, you never know.
All right. So what do we need to do? What do we need to do? One, we need to. All right. How about this? What is it we need to do in push?
We need to create another array. We need to increase my M capacity, create another array with the new M capacity.
All right. But before we do that, we need to see if we need to do that, right?
Check this out.
Yeah. If, yeah, so 1, check if the stack is full. 2, if full, increase capacity. All right, 1. By the way, guys, it's very helpful to write your pseudocode as comments and then make it happen. All right, so how do we check if the stack is full? If. Yeah. Well, if it's equal to, and again, I'm going to do a defensive coding. You never know, mtop might all of a sudden be like 5 times higher, whatever. All right, while or if, we need to, if full, increase capacity. To make your code easier to read, I highly recommend you make a private function. Public, or not public, sorry. Void increase capacity. Notice I made it private. What does that mean? One that this class can call, but can anyone else? No. All right, so I'm going to go into this, into this code, increase capacity. Now this function's easy to read. Great. How do we increase the capacity? Well, what do we do first? Yeah, so we're going to create a new temp. How big should we make it? Oh, did anyone tell you?
Tell you what, did the bird's the word?
Bird. Okay, so we could do, yeah, we could do m capacity plus plus, and let's go ahead and do it that way. Equals new m capacity.
You can just like put the pluses.
Sure, hold on. I'm going to write it this way and it'll be clear why in a moment. I'm going to go and create a little temp int old capacity equals m capacity. Increment, yeah. And then after we've got our new temp, we need to actually copy everything over. I'm going to go ahead and speed this up just a little. Capacity, I++. We're going to go ahead and copy all that stuff over. I don't know why I called it temp, but that's, you know, that's fine. M stack sub I, and then once we're done with that, we'll have m stack equal m temp. And we forgot to do something.
Delete the.
Yeah. There we go. Okay. I wrote this out real quick, just so you understand. We first keep track of what the old capacity is, so that we know how many elements we need to copy over, so we don't do it invalid reads or writes. We increment the capacity. Right now we're incremented by 1. We're going to create a new temporary of the array with the new capacity. We're going to copy all the elements over, delete the old stack, and then update the current stack pointer to point to the new stack, or new array of integers. Yes?
Why delete m stack but not m temp?
Because m temp is going to be the new stack. So m temp is replacing the old stack. So we still need to use it, and it will be deleted during the destructor. Good question. All right. So this code should work, actually. Let's see if it does. There it goes. It did work. But, let me see. But there is a significant issue. If I add another 0 here, let's see what happens. Okay. It's actually running really, really slow. Why is it running really, wow, it's running really slow.
Well, just to like create and delete arrays every single time you add after it reaches 32.
Yeah, so it's constantly creating a new array. What was your?
I was going to say it's not doubling in size every time.
All right, so there are different ways to go about and fix this error. In general, you don't want to just increment incapacity by 1. You want to usually multiply it by something. It's common to choose between 1.5 and 2. When you want to increase the size of an array, it's very common to either increase it by 50% or 100%. And the reason for that is usually if you increase the array, you need to increase the size of array, you're probably going to need to use that data again fairly soon. So by multiplying it, you're actually going to greatly speed up your code. For example, oops, we'll go ahead and run it now. All right, everyone saw the difference there? I can run time and show you it was probably what, like 30 seconds versus less than 1, but I think the point hopefully has been made with that. Yes.
Why don't all capacity we can just like use m capacity divided by 3, for example?
Why? I'm sorry. Ask that again?
Oh yeah, because you have to change it in only one, for example.
Yeah. Oh, yeah.
So if you use, for example, m capacity times 1.5, you wouldn't have to change it in the for loop.
Right, because we're still using old capacity. Yeah. Okay. Good questions. Any others? All right. So that was one stack implementation. And we've already written some code. Look, we have test cases. Okay. I'll just go stop the video.